Good morning. I'm Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the course Atomic and Molecular Spectroscopy. Today we are going to discuss quantum states and spectroscopic terms. This is the part 2. So in our earlier lecture, we already discussed the total angular momentum, which precises about the magnetic field direction. See here, in general, for a single electron atom, we can see orbital angular momentum in this direction. L bar is the orbital angular momentum vector, and S bar is the spin angular momentum vector. So these two vectors add up in the vector method and gives rise to total angular momentum vector J bar. And again here, these two vectors makes precision about J bar. L bar and S bar makes precision around J bar. That means the axis of rotation is along the direction of J bar. And this J bar, total angular momentum vector, makes precision about B bar, applied magnetic field direction. So, as we discussed in the earlier lecture, the total orbital angular momentum J bar will be obtained by vector summation of L bar and S bar. So J bar equal to L bar plus S bar. We already calculated the magnitude of J bar also by taking square of these terms. So squaring on both sides, we will get L bar plus S bar whole square. So this gives the magnitude of J square equal to L square plus S square plus 2 into L bar dot S bar means 2 LS into cos theta. Here theta is the angle between L and S, L bar and S bar. And so that the angle between L and S can be determined by simplifying this equation. L bar S bar equal to J square minus L square minus S square by 2 into L and S. So the magnitude of J bar, as we have already calculated, given the value of J, the magnitude of J bar equal to square root of J into J plus 1 h by 2 pi, and L, the magnitude of L is square root of L into L plus 1 h by 2 pi, and S, the magnitude of S bar equal to S into S plus 1 h by 2 pi, whereas J is also called internal quantum number. L is the orbital angular quantum number, S is the spin angular quantum number. So by substituting all these values, we can get J into J plus 1 h by h square by 4 pi square. So we can take this into outside of this entire expression. So we can write later, minus L square, L into L plus 1 minus S into S plus 1, and we can also notice that there are terms the magnitude of L bar and S bar in the denominator. So the terms, otherwise let us write here h square by 4 pi square. In the denominator, 2 into square root of L into L plus 1, square root of S into S plus 1, and h square by 4 pi square. These two terms cancel each other. So the angle between cos L bar and S bar can be determined by knowing the values of this, right, some little down. Cos L bar, cos of angle between L bar and S bar is equal to J into J plus 1 minus L into L plus 1 minus S into S plus 1 by 2 into square root of L into L plus 1 square root of S into S plus 1. This is the angle, cosine of the angle between L bar and S bar. And again, the values of J, if you know J value as like orbital angular momentum quantum number, if you know J value, we can find MJ values also. MJ values. So the possible MJ values can be uh, J, J minus 1, J minus 2, etc. 0, 1, 2, up to no, minus 1, minus 2, minus J, up to minus J. Okay. So there could be values of MJ from J to minus J in steps of integer values. Integer values. So in general, here we can also notice that uh, the magnitude of Jz is also equal to Mj into h by 2 pi. Mj into h by 2 pi. So the values of Mj are like this. And again, we also can notice that J value, J must be equal to L plus or minus S. L plus or minus S. So here in general, S can have values 1 by 2. So J must be equal to L plus of and L J equal to L minus of. So there could be two possible values for J for any L value. So it depends on orbital angular quantum number. Orbital angular quantum number L value. Okay, so this type of splitting occurs with the inclusion of spinning of electron. So the total orbital quantum number changes with the spin quantum number. Okay, So all these are represented by the vector here, j bar. The orientation of j bar also can change with the orbital orientation and spin orientations. Okay, so with changing the spin orientation, the energy values of electron slightly changes from the earlier. That means that is with the orbital momentum. So that's why these uh, energy values, that means orbital orientations with the different energies, with the smaller separations, are denoted by quantum states, separate quantum states, and these quantum states also indicated with terms uh, that are called terms, spectroscopic terms. So let us see how we should uh, give the notation for spectroscopic terms for different quantum states of electron. So the quantized energy states, those are also called quantum states of an atomic electron, are described in terms of the quantum numbers n, l, s, and j. In earlier lecture, we discussed that the quantum state of electron can be described by n, l, ml, ms. So now we can describe the state of the electron by n, l, s, j. These are newly added quantum numbers, j, with the inclusion of we can say that spin orbit interaction. J comes up with the spin orbit interaction. So the electrons having orbital quantum number, for example, can have values 0, 1, 2, 3, 4, and these are orbital those orbitals having quantum numbers 0, 1, 2, 3, 4 are designated by sp, d, f, g respectively. For L equal to 0, the orbital is designated by S. For L equal to 1, the orbital is designated by P. For orbital 2, L equal to 2, it is designated by D, so that we can give designations for different orbitals having different L values. So the atomic states in the atom are specified by writing the corresponding principal quantum number along with these numbers. So in general, different orbitals with the principal quantum number can have different orbital angular quantum numbers also. So in general, for n equal to 0, the value of n equal to 1, the value that can be available for L is only 0. For n equal to 2, the L value could be either 0 or 1. So here, for an electron which have n equal to 2 and L is equal to 0 is a 2s atomic state. The electron principal quantum number is 2. That means the electron is in the second orbit of the atom, starting from that means if it is the nucleus, this is the first orbit of the electron, that means n equal to 1, second orbit of the electron n equal to 2. So here the orbital quantum number L is 0, then that particular electron can be indicated by 2s atomic state state of the electron is indicated by 2s atomic state, and one for which n equal to 3. If n equal to 3 and L equal to 1, if L equal to 1 and the orbital principal quantum number n equal to 3, then that particular state is called 3p atomic state. 3p atomic state. So this is the indication of atomic states regarding principal quantum number and orbital quantum number. Still, even though this atomic state, 3p atomic state, can be exhibited by several other electrons also. It is not exhibited by single electron. So we need to differentiate or distinguish between those electrons. So for that means the energy of those electrons will be slightly different. And the energy levels of electrons of an atom are called terms of the atom. The different energies, energy levels, those energy levels are termed as terms of the atom. Terms of the atoms, and the corresponding energies expressed in wave number are called term values. The energy states, the energy levels, these levels are called as terms, and the energy values in terms of wave number are called term values. Okay. For a 1 electron atom, the energy levels corresponding to 0, 1, 2, 3, 4 are represented by SBTFG respectively. So by spin orbit interaction, each energy level of a given L is split into two sublevels. So whenever orbital angular momentum is interacted with spin angular momentum, that means spin orbit interaction comes into the picture. So whenever we consider spin magnetic spin angular momentum also, so that gives splitting of orbital angular total angular momentum. So that gives for each L value we can see two sub levels. So L is split into two sub levels, with the exception of S term. That is also with the exception of S term, because for S L equal to 0, so for which J is equal to 1 by 2 only. Here 1 by 2 only. So because here in general J equal to, you should write L plus S or L minus S. There could be two possible values for J whenever spin orbit interaction occurs. So in general here for S term, L is for S term, that means S orbital. That means L is 0 for the orbital angular momentum, then S is that means S. L equal to 0 means S. The term is called S, represented by S, and if it is L equal to 0, the J value should be 0 plus of or 0 minus of. And again here we must notice that there should be no negative values for total angular momentum. So there could be only 1 by 2 value. The value of J could be only 1 by 2. There should be no two values. That means there is no splitting for the S term particularly for L equal to 0. The remaining terms either P, D, F, all these terms can be having splitting into two separate sublevels. So the number of different possible orientations of L and S and hence the number of different possible values of J is known as multiplicity. So each generally here for single electron atom, uh, the term P can have two sublevels. That means splitting can be in uh, two sublevels, and D also two, F also two. That means all these are that means J can have two values. So the number of different possible J values is called multiplicity of the term. So it is equal to 2s plus 1. It depends on the s value, 2s plus 1. So the multiplicity is given by 2s plus 1. So for the electron, generally S is equal to 1 by 2. So for the single electron atom, 2 into 1 by 2 plus 1, that is equal to 2. So the multiplicity for single electron atom, whatever the term, must be equal to 2. So now if we consider multiplicity, in general we should write multiplicity as the superscript, left side superscript to the term. If it is S, we should write like this. If the term is P, the multiplicity for the single electron atom is 2, so we should write 2P. For the term D, we must write 2D. In this way, we should indicate the term value left top corner, top superscript to the term. So these are also called doublet terms. If the multiplicity is 2, then it is called doublet terms. And if that multiplicity is 3, that will come when there are more number of electrons in the atom. But for single electron atom, there could be only two terms, two values for J, and it is called doublet. So in addition, the J value is added as a right subscript. Right subscript. For example, uh, if we consider L value 2 for any single electron atom, then S value is 1 by 2. Then J value for this particular state of the electron must be having two values. One is L plus S and another one is L minus S. So that means 2 plus of and 2 minus of. 2 plus of and 2 minus of. That means 5 by 2 and 3 by 2. Then how we should represent the spectroscopic term means here we should write first the designation for L equal to 2. So that is 2 means D. Here we should remember for L equal to 0, the term is S. L equal to 1, the term is P. L equal to 2, D. 3, F. So, as L is equal to 2, the term representation is D, and again, as S is equal to 1 by 2, the multiplicity is 2, we should write here 2D. And again, write subscript, we must indicate the value of J. So 1 is pi by 2. So there is another energy value or term that is represented by 2D 3 by 2. So that means there are two terms for the electron having value L equal to 2 and S equal to 1 by 2. There are two terms. These two are energy levels. There are two energy levels for the electron having values L is equal to 2 and S is equal to 1 by 2. And again, if the principal quantum number is 3, then we should indicate principal quantum number in front of the spectral terms. These spectroscopic or spectral, we sometimes call spectroscopic terms as spectral terms also. So we should denote like this. So this is the principal quantum number. Okay. So if there is any spectroscopic term, for example, like this, 2 2p 1 by 2 means here 2 is the principal quantum number, that means n is equal to 2, and here s is equal to 1 by 2, l equal to, as there is a p as the term, so l value is equal to 1. Okay, so these are the observations we should do by seeing the spectroscopic term. And if there are several electrons for an atom, then the representation of spectral terms is again a little complex. Why? Because if an atom containing several electrons, the orbital angular momentum of individual electrons can be having quantum numbers again 1, 2, 3, etc. Either it is 0 also, 0, 1, 2, 3. No. Li values, whereas I equal to 1, 2, 3, etc. for individual electrons. So then to find out the total or resultant electron orbital angular momentum, we need to add up individual angular momentum, orbital angular momentum of the electrons, all electrons. And then after finding the individual total orbital angular momentum, then the magnitude will be given like this. Here L is the total orbital angular momentum. So square root of L into L plus 1 h by 2 pi. So that means L is the orbital quantum number for the atom, entire atom. So after including the all electrons, for the all electrons. Similarly, we should, if there are the electron can have several as the atom is having several electrons, spin quantum number for all electrons may be indicated by SI, whereas I equal to 1 to 3, etc. Then to find out the total or effective or resultant spin angular momentum, then we must add up to S, and then the magnitude of spin angular momentum can be calculated by square root of S into S plus 1, whereas S is the spin quantum number of the atom. And then after finding the total orbital angular momentum and spin angular momentum, total spin angular momentum for entire atom, we need to add up these two values to give up the total orbital and total angular momentum J. Actually J bar vector is a vector. And to find out the magnitude of orbital angular momentum, total angular momentum J bar, we need to use the formula square root of J into J plus 1, whereas J is the orbital angular momentum, orbital angular momentum quantum number, and it is also called inner quantum number for the atom. Inner quantum number for the atom. So the terms of the atom may now be singlets or doublets or triplets, because we are adding S values for individual electrons if there are several electrons in the same direction. That means 1 by 2. So if there are 4 electrons, each electron can have 1 by 2, 1 by 2, 1 by 2 S values. So whenever we add up, the spin quantum number will give 4. So if we find out the multiplicity 2s plus 1, maybe we can indicate the multiplicity by m. So m equal to 2s plus 1, that is 2 into 4 plus 1. Then the multiplicity becomes 9. So that means 9 individual times can available for that particular atom. Okay. So, and again we can find individual orbital angular momentum quantum numbers also after adding up all the electrons, regarding all the electrons, and we can find J values also. So we will see how to represent the spectral terms for multiple electron atoms in the next lecture. So these are also denoted in the same way as the terms of one electron atom, as like we denoted like this, some 2d 5 by 2, 2d 3 by 2, including the principal quantum number. Maybe sometime the same terms can be available in the other principal quantum number, or that means other orbit also. The same terms can be available in other orbit also. That means principal quantum number can change. There could be 4 also, 4, 5, any number. So by seeing the term expression for term, we can identify the principal quantum number, multiplicity, and J values, and again L value. all these things can be indicated in the spectral term. So this type of indication or notation is used for the distinguishing of energy levels for any atom, either it is single electron atom or multiple electron atom. So we see the spectral term notation uh, uh, for multiple electron atoms in the next lecture by taking with some example also, because in general here we need to, by taking L value, S value for different individual electrons, we may need to add up to find out the total spin angular momentum and total orbital angular momentum, and then we need to add up individual j values also, and then total j value, total angular momentum, quantum number j value. So we'll see all those things in the next lecture. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.